Hello everyone. So today I'm gonna cover single fluid pipes. We're gonna cover three type of problems that you might have in this single which uses single fluid pipes. So I'm gonna go through all. First of all, I'm gonna draw a table in which I'm gonna show all these three type of problems and which unknowns are in these problems that you need to solve, and which known parameters are these problems. And after that, I'm going to solve one example for each these three type of problems. So with this, you should be able to kind of solve any problems related to these single fluid pipes. And these single fluid pipes. And after that, for doing this, we are going to use, just to refresh your mind, we are going to use some of the things that we learned before. For example, we are going to use major losses or minor losses that we kind of covered in the previous section of the course. So these will be some kind of things that we are going to use here. And if you remember, the major loss was where we kind of derived it through some dimensional analysis, as well as some the Buckingham pipe theory. So we found that the major loss in pipes, which shows kind of the pressure drop in a pipe flow, depends on the Reynolds number and also the roughness of your pipe element. And to do that, we showed it's kind of related to, if you remember, it's kind of related to, we showed that with Moody diagram. So if you remember Moody diagram, that I also distributed in the class, kind of with using that, we can find the major losses. Also, I showed you an estimation of Moody diagram, which was through some other equations. So for example, Holland's equation was one of them, in which we were kind of estimating the Moody diagram. And the Moody diagram, if you remember, was relating these the Reynolds number and roughness length in a fluid problem with the friction factor. So you can get the friction factor from this Moody diagram, and then you based on that friction factor, you can calculate this kind of the head loss, the major head loss in your system. Okay, so this is kind of an overview of what we did before. And now I want to, so let me just as a reminder, if you remember, we showed that HL major, which is kind of the major head loss in the system, we defined it as F, which is a friction factor, times L over D. L is the length of the pipe, D is the diameter of the pipe, multiplied by V square, which is the velocity of the pipe, over 2 times G, where G is the gravitational constant. Okay, so this was the major head loss in our system. And if you remember, the minor head loss, for minor head loss, it really depends on we didn't come up with a kind of single formula for that, because all the additional components like valves, bends, or tees can add to the overall head loss of the system, and it's very difficult to find this theoretically, and most of these are based on some experimental data. However, we found a kind of estimation for a sudden expansion, if you remember, and so but in general you can define the HL, the head loss of the minor head loss as KL, which is a loss coefficient, multiplied by V square over 2G. So very similar to that, but for this KL we usually use experimental data for that. And so today I'm going to talk about 3 different problems that we might have in this kind of framework for single fluid pipes. So first I will show the table where we can find what are these different 3 type of problems that we can have for this single fluid pipes. So let's draw a table to see what we have here. So excuse me, let me remove this one. Okay, so we have a table, and I'm gonna draw it here. So we can have 3 type of problems. So as you can see, let me draw it here. Okay, so 1, 2, 3, and 4. Okay, so let me now draw here one, 2, 3. Okay, I think I made one more, so let me draw this here. Sorry for that. Okay, so we have now 3. Let's see here. So here we have the variable in our system, and then here we have type 1. So this is type 1, and then we have type 2, and type 3. Okay, so we have 3 types of problems, and we have pipe, the first variable is pipe diameter, which we will show it with D. Okay, so this is the first variable, and then the second variable that we have is flow rate, which we show it with Q. And then the third variable that we have is delta P or HL, or pressure drop or head loss. Okay, so pressure drop or head loss is our third variable. So this one we can show with HL. Okay, so now let's see what does this mean. So this means let me draw this. So here for type 1 we have for type 1 problem we usually have pipe diameter, we have flow rate, but we don't know what is the head loss. So we are given these pipe diameter and flow rate, we want to find what is the head loss or pressure drop in the system. Okay, for type 2 problems we have pipe diameter, we have head loss, but we don't know what is the flow rate or Q in our problem. So we want to find this flow rate in the system for type 2 problems. And for type 3 problems, we don't know what is the pipe diameter, and we have the flow rate and head loss in the system. So this is kind of a design problem. So we want to find the best, the diameter in which it can have this specific flow rate, and given some specific pressure drop in the system. For example, if you have some major and minor losses in your system, you calculate that, and then you want to design the pipe diameter. So this is kind of the type 3 problems that we are going to have. Okay. So now that we talked about this 3 type of problems, for the next step, I want to go and solve one example for each problem. Okay, so let's start with this one. First, let's remove everything. Okay. Okay, so the first example I want to solve is for type 1, where we have the pipe diameter and flow rate Q, and we want to find the pressure drop in the system. Okay, so let's start. Example type 1, determine the pressure drop or del P. Okay, delta P in the system. Okay, so the problem says determine the pressure at point 1 if A, all losses are neglected, B, the only losses included are major losses, and C, all losses are included. Okay, so this is a problem statement. So let's see how the problem looks like. I want to copy the file here. So here I have copied the problems statement as well as the picture here. So this, as you can see, is a pipe system. It's a single pipe system. So here the length of the first part, we have like a flow rate at the beginning, which is 0.0267 foot cube per second, which enters the first pipe at section 1 here. The length of the pipe is 15 foot, and then we have this bend, and after that we have this 10-foot pipe, and then here we have the second bend, and then we have 5-foot pipe, and then here we have 10 foot, and then we get to a wide open valve, and after that we have like 10 foot, and at the end we get to a tap in which it's the KL or loss coefficient for that is 2, and it has 0.5 inch diameter, and the pipe diameter is 0.75 inch, which is 0.0625 foot. This is again the Q, which the flow rate at the beginning. The type of the pipe is copper or drawn tubing. The density of water is 1.94 slug per foot cube. The viscosity of the water is 2.34 times 10 to the minus 5 pound second per foot square. Okay, so this is kind of the problem that we want to solve, and this is type 1 problem. So as you remember, we have the pipe diameter here, the flow rate, and we want to find the pressure drop in the system, and also the loss in the head loss in the system. Okay, so the question wants us to find the pressure at point 1, which is here, for 3 conditions. First, if all losses are neglected, so we just neglect any loss and think, okay, there is no major or minor losses. The second one, only losses included are major losses, so we only calculate these pressure drops across these pipes. And then the last one is all losses are included, which means that we also include the minor losses, which are caused by these joints, these bends, and this open globe valve, and this one here, which has a the KL or loss coefficient of 2. Okay, so now that we have seen the problem, we can start solving that. So let me just remove some stuff. I want to remove here this, and let's just put it here for our reference. Okay, put it here just so you remember what it is. Okay, so we start with the answer. So answer, let me just make this. First, you have to calculate Reynolds number, because this is required especially when we want to solve all the losses in the problem. And first we do some pre-calculations, like to find losses in the system, and then we start to write the energy equation to find the pressure at point 1. Okay, so first we want to find the Reynolds number. Okay, so if you remember, V1 is Q1 over A1. Okay, so based on this, we can find 0.0267 foot cube over second over pi. So it's 3.14 times d square. So let me write it d square, because it's going to be a, so it's going to be d square over 4. So d is 62.5 foot square over 4. So if you calculate this is going to give you 8.57 foot per second. Okay, so this is the first part. To find, first we need to find the velocity in the system, and then I want to find the Reynolds number, because other than that I have almost everything. Okay, so if you remember, the Reynolds number is rho v d over mu, which is viscosity. So density times velocity times d, the diameter of the pipe, over mu, which is the viscosity, is going to give us the Reynolds number. So we can calculate it here, and I'm going to show you the results here in a better way. Okay, so we got the Reynolds number. So now let's go through the calculation. So this is the Reynolds number definition, rho v d over mu, as we mentioned. And so we now just plug in the numbers in the problem. So we have rho of water from here, 1.94. We have the velocity where we found 8.7 foot per second times the diameter of the pipe, which is given in the problem, 0.0625 foot, over mu, which is the viscosity of water, which is also given in the problem, 2.34 times 10 to the minus 5 pound second over foot square. So if we calculate the Reynolds number and plug in the numbers, it's going to give us 45,000. So as you remember from the Moody diagram, 45,000 is in a range where the flow is turbulent. So we clearly know that the flow here is going to be turbulent, and so we have to use the Moody diagram and know the roughness of the pipe as well as the Reynolds number in order to be able to find the head loss in the major head loss in this pipe system. Okay, So, well, now let's write the energy. We want to find P1 here, the pressure at point 1, if you remember. So, in order to do that, we write the energy equation. So, this is the energy equation between point 1 and 2. So, this is point 1 and this is point 2. So, the entrance is point 1 and the exit of the fluid is at point 2. So we write the energy equation, P1 over rho g plus alpha 1 v square over 2g plus z1 equals to P2 over rho g plus alpha 2 over times v2 square over 2g plus z2 plus head loss in the system. So gamma or rho g for water we know is 62.4 pound per foot cube. Z1 is 0 if you remember, and Z2 is 10 foot plus 10 foot, which is going to be 20 foot in the problem. And P2 is pressure at point 2 is at free jet, because here is just the vicinity of the atmosphere, and so the gauge pressure here is going to be 0. So we just write all these numbers and then plug them into our energy equation. The other assumption that we make is that the kinetic energy coefficients of alpha 1, so these are the kinetic energy equations, if you remember, alpha 1 and alpha 2 are unity here because the flow is turbulent, and the velocity distribution in a turbulent flow is nearly uniform. So here I have written this. So we assume that these energy coefficients alpha 1 and alpha 2 are unity because the flow is turbulent, and the velocity distribution in a turbulent flow is nearly uniform, if you wish. So the velocity uniforms are nearly uniform in a turbulent flow. So we assume that alpha 1 equals alpha 2 equals to 1. And so the other thing is we can calculate V2. So V2 is the velocity here at the exit. So V2 is gonna be Q over A2, and the Q is constant here because of the conservation of mass. So this is given in the problem, which is 0.0267 foot cube per second over P over 4 pi over 4, the area of that 0.5 over 12 square foot square. So if you remember, the diameter here is 0.5 inch, and so by dividing it by 12 we converted to foot, and then this is going to give us V2 is going to be 19.6 foot per second. Okay, so now based on all these values that we found, we can plug all of these into the energy equation and find a relation for P1, which is the unknown in this problem. So P1 is going to be rho g times Z2, and Z1 is 0, is going to cancel, plus 1/2 rho V square minus V1 square plus rho g times HL. Okay, so we multiply everything by rho g, and the other thing that we made is we assumed alpha 1 and alpha 2 equal to 1 because the flow is turbulent, and we have V2 and V1 here. Also we know V2 is 19.6 foot per second and V1 is 8.7 foot per second. And rho g is just gamma. We know gamma here, and we have Z2. So we know almost everything here except HL. Okay, so we don't know the head loss yet. So the first part of the problem is simple. It asks if find P1 if all head losses in the system are neglected, or in other words, if HL is 0. So we go to calculate this. So P1 is going to be rho g, which is gamma, 62.4 pound per foot cube, times 20 foot, which is the Z2, plus 1/2 times rho 1.94 slug per foot cube times v square, v2 square minus v1 square. So v2 is 19.6 foot per second square minus 8.5, which is v1 square, equals to, so if you plug all these number here, so you get 1,248 plus 299 pound per foot square, which is gonna give us 1,547 pound per foot square. So this is gonna be our pressure at point 1 if there is no head loss in the system. So 1,547 pound per foot square equals to 10.7 psi. So this is going to be P1 if we don't have any head losses in the system. So now let's go to the second part of the problem, which deals with when we have the only losses in the problem are major losses. Okay, so if the only losses in the problem are major losses, we can calculate the major losses based on this formula which is shown here, which is HL equals to F times L over D times V1 squared over 2G. Okay, so first of all, we want to find what is the friction factor. Okay, we want to find friction factor, and this is a turbulent flow. All the other things we know, and the only unknown here is friction factor. So in order to find a friction factor, we can use Moody diagram, but for Moody diagram we are gonna need two parameters. First, the Reynolds number, in which we calculated, is 45,000, and then the second one is the roughness of the pipe. And so in order to find the roughness, we go to table 8.1 of the book, and roughness is 0.75 inch diameter copper for a 0.75 inch diameter copper pipe, which is drawn tubing pipe. You find that the epsilon or roughness is going to be 0.00005 foot. Okay, so now we can find the relative roughness by dividing epsilon over the roughness over the pipe diameter, and if you calculate that, it's going to give us 8 times 10 to the minus 5, and then we also have Reynolds number, which is 45,000. Okay, so from Moody chart we can use either Colebrook equation or Holland equation, or from the Moody chart we can find F, which is the friction factor here, which is going to be 0.215. So I'm just going to show you how you can use Moody diagram here. So you have the Reynolds number here. So Reynolds number is 45,000. So it's going to be somewhere. So it's going to be 4 times 10 to the 4.5 times 10 to the 4. So we have to go here, and then so it's going to be somewhere around here. We go up, and then we have the roughness length. The relative roughness is 8 times 10 to the minus 5. So 1, 2, 3, 4. So this is 1 times to the minus 0.5, and this is 10 to the minus 3, and this is 8 times 10 to the minus 4, 4 times 10 to the minus 4, this is 1 times 10 to the minus 4, and this is 1 times 10 to the minus 5, this is 5 times 10 to the minus 5, so it should be somewhere around here, and then we go up, so we follow this line to, we go around here, right? So it should be somewhere around here, and based on this, if you go to the left, you will find it should be around, which is something right, which is around 2.17. Okay, so it's gonna be somewhere around here. So because this is 0.02 and this is 0.0225, so it's gonna be somewhere around here. Okay, so this is how you find friction factor from Moody diagram. And now that we have the friction factor, we can calculate this head loss, which was the only unknown in this equation that we had. So the other things are similar to before. Rho g p1 equals to rho g times z2 plus 1/2 v2 square minus v1 square, plus now we have rho times g times the head loss, and the head loss is this FL over d v1 square over 2g. So this we calculated from the previous part, which is going to be 1,547 pound per foot square, plus the new things. The one is rho is 1.94 slug over foot cube times the g 0.025 times L. So the total length of the pipe is, we have to put the total length because we want to find the major head loss in all the system. Is going to be 15, so we can calculate it here. Let's look. So it's going to be 15 plus 10 plus 5 plus 10 plus 10 plus 10. So if you add all of this is going to give us the total length of the pipe, which is going to be 60 foot. So we put it here, 60 foot, and then we have, so we have F times L, which is the total length of pipe, is 60 foot, over D, and D is given in the problem, which is 0.0625 foot, multiplied by V1 square over 2G. So V1, if you remember, V1 we calculated it is 8.7 foot, 8.7 foot or second square over 2, and if you calculate this part, all this head loss is going to be 1,515 pound per foot square. So we add this to the 1,547 from other things like the elevation change and also this kinetic energy change. So it's going to give us 30,062 pound per foot square, which equals to 21.3 psi. So if we have the major head loss in the system, the pressure drop is gonna equal to 21.3 psi in the system. Okay, so for the next part, I'm gonna solve if we have all the losses in the system. So this is only where we have the major losses in the system, and now we also want to calculate and include the minor losses in the system. Okay, so section C asks if major and minor losses are included in the system. So if major and minor losses are included, the energy equations become something like this. P1 equals rho g z2 plus 1/2 rho v2 square minus v1 square, plus this is the major loss in the system, which is F rho g times the total length of the pipe the system L over D times V1 square over 2G plus sum of all minor losses in the system, which is rho KL V square over 2. Okay. So the first part, these all we know we found from section B is going to be 3,062 pound per foot square, and then plus the sum of rho KL V square over 2. So in order to find the head losses in the system, we have to go through all the valves, the bends, and all elbows, the open globe valve, the faucet at the end. So we have to go through all of them and then find their corresponding loss coefficient for all of them, and then sum them together. So we have to find the head loss for this faucet here, this open globe valve, and also for all these elbows. Okay, so we need to find all these the head loss for all of these, and then sum them all to find the total head loss in the system. Okay, so in order to do that, we need to go to some tables. So table A2, which I distributed before in the class, if you go through that, you find that KL for each elbow is going to be 1.5. The loss coefficient for the wide open globe valve is pretty large, is 10. The loss coefficient for the faucet is gonna be for 2, which is also given in the problem. So this is the only head loss in the system which is given. So KL in the problem is given 2, and the rest we find from that table 8.2. Okay, and now if we calculate the sum of all these minor losses, it's going to be rho KL times V square over 2, which equals to 1.94 slug over foot cube times V square over 2. V square is 8.7 foot square over 2 multiplied by KL, the sum of all KLs, which is gonna be 10, which is for the wide open globe valve, plus 4 times 1.5, because we have 4 elbows, plus 2, which is for the faucet. So let's go back to the problem to see again. So we have 4 elbows, 1, 2, 3, 4. So we have to multiply 4 by that. We have 1 open globe valve, and we have 1 faucet. So the pipe length is constant all here. So that is why we can use the V at the beginning. And it's only at the faucet where the D or the diameter changes. So we have V2 around there. So we use V1 square here, which is 8.7 foot square over 2. And if you calculate all these minor losses, you will get 1,321 pound per foot square. So P1 is gonna be 3,062 plus 1,321, which finally it's going to be 4,383 pound per foot square, which equals to 30.5 psi. So if you have all major losses and minor losses in your problem, the pressure drop in the system, in this pipe system, single pipe system, is going to be 30.5 psi.